All right, so let's dive into something truly mind-boggling. Imagine a world where, like, a snowman never melts, where things just stay perfectly ordered forever. We're talking about the world of zero-entropy materials, where the impossible seems to become possible.
Yeah, it's a fascinating area. It really challenges our everyday understanding of how the world works. We're so used to things naturally moving towards disorder. Just think about like a messy room, a melting ice cube, or your coffee going cold. That's entropy in action.
Exactly, and it always takes energy to bring things back to order, right? So zero entropy, meaning perfect, unchanging order. It feels like it's breaking some fundamental law of nature.
It certainly seems that way, at least at first glance. But what's really remarkable is how quantum mechanics comes into play, especially at these extremely low temperatures near absolute zero.
Absolute zero. Now, that's seriously cold, isn't it? Could you remind us what kind of temperatures we're talking about here?
Oh, yeah, we're talking about negative 273.15 degrees Celsius. At those temperatures, atoms practically stop moving, and they can form these incredibly organized structures, these perfect crystals. They basically settle into their lowest possible energy state, what we call the ground state.
Okay, so help me visualize this ground state. What's a good way to think about it?
Imagine like a spinning top. As it loses energy, it spins slower and slower until it eventually comes to a complete stop, right? That final resting state. That's kind of like the ground state for atoms. It's the point of lowest energy. And it would take additional energy to get them out of that state.
So atoms near absolute zero are like the stop spinning top, just hanging out in their lowest energy state.
Exactly. But here's where things get really strange. Even at this lowest energy level, there's still a tiny bit of residual energy, what we call zero-point energy, and some bizarre quantum phenomena, like quantum tunneling, become dominant.
Quantum tunneling. Now that sounds intriguing. What exactly is that?
Well, imagine you roll a ball up a hill. In our everyday world, we expect the ball to roll back down, right? But in the quantum world, there's a chance that the ball could tunnel right through the hill and appear on the other side. It's as if it defied the laws of classical physics.
So in this ultra cold world, atoms can basically teleport through barriers.
Hmm.
That's pretty wild. And are these zero-point energy and quantum tunneling? Are they just theoretical ideas? Or have scientists actually observed them?
Oh no, these are real observable phenomena. Scientists have actually devised these incredible techniques to reach these ultra-low temperatures. They use things like laser cooling, where lasers are used to actually slow down atoms, and also magnetic trapping, which confines atoms using magnetic fields.
So it's not just about having like a superpowered freezer. It's about manipulating these atoms with incredibly precise tools.
Exactly. And by creating these conditions, scientists have made some truly groundbreaking discoveries, including time crystals.
Time crystals. Okay, you're going to have to explain this one because it sounds like something out of a science fiction novel.
It does, doesn't it? Time crystals are structures that have this repeating pattern in time. They're constantly changing, oscillating in a predictable way, but remarkably, without consuming any energy.
So they're in perpetual motion, but without any energy input.
Yeah.
Doesn't that violate, well, everything we know about physics?
It would violate the laws of physics as we know them, at least in our everyday world. But remember, in the quantum realm, different rules apply, and time crystals exploit these quantum rules to achieve this seemingly impossible feat.
It's mind-blowing that we're talking about materials that could potentially defy the very laws of thermodynamics. And time crystals aren't the only type of zero-entropy material out there, are they?
Right. There's another fascinating class called topological materials. These materials have unique electronic states that are incredibly stable and resistant to errors.
So if time crystals are all about perpetual motion, topological materials are about ultimate stability.
That's a great way to put it. They're like having a fortress for information, protecting it from any corruption. And this stability opens up incredible possibilities, especially in fields like computing and information storage.
Okay, I'm already starting to imagine the potential applications here. But before we get too carried away, why don't we take a moment to really unpack what these incredible zero-entropy materials could mean for our future? We've talked about the what's, but now I'm really curious about the so what. What are the real-world implications of all this? So we've got these incredible materials, time crystals, and topological materials that seem to bend the rules of physics as we know them.
Yeah.
But how does this translate into actual tangible benefits for us? Where do we see the biggest impact of these discoveries?
Well, the potential applications are vast, spanning from computing and energy to medicine and transportation. Let's start with computing. Imagine a world where computers could perform calculations that are currently impossible, even for like the most powerful supercomputers.
What kind of impossible calculations are we talking about?
Well, think about simulating complex molecular interactions, to design life-saving drugs, or modeling the intricacies of climate change to find solutions for a sustainable future. These are problems with enormous computational demands. And even with our current technology, they can take years, if not decades, to solve.
So we're talking about tackling some of the biggest challenges facing humanity. How exactly would zero-entropy materials change the game?
Quantum computers, built using these materials, could leverage those unique quantum properties we discussed earlier, things like superposition and entanglement, to perform calculations exponentially faster than traditional computers. We're not just talking about a slight speed boost here. We're talking about solving problems that were previously considered unsolvable.
That's incredible. It's like having a key that unlocks a whole new realm of possibilities. And what about energy? I remember you mentioned batteries that never die. That sounds pretty appealing in our energy-hungry world.
Absolutely, with zero-entropy materials. We could create energy storage devices with like unparalleled capacity and efficiency. Imagine batteries that hold a near infinite charge, transfer energy without any loss, and never degrade over time.
Okay, that would be revolutionary. No more range anxiety for electric cars, no more scrambling for a phone charger. But how would this impact something as massive as our power grid?
Well, the implications for our energy infrastructure are profound. Imagine a power grid where energy is transmitted without any loss due to resistance. We could harness renewable energy sources like solar and wind with unprecedented efficiency, storing that energy for use when needed and distributing it seamlessly without waste.
So we could have a truly sustainable energy system, powered by clean sources and free from the limitations of our current infrastructure. It's hard to even grasp the magnitude of that shift. But let's shift gears a bit and talk about medicine. What kind of medical miracles could these materials enable?
One of the most exciting areas is the development of ultra-precise biosensors using time crystals. These sensors could detect the presence of specific molecules in the body, even at incredibly low concentrations, with incredible accuracy.
So we could potentially diagnose diseases at their earliest stages
Mm-hmm.
before any symptoms even appear. That's a game changer for early intervention and treatment.
Exactly. And because these materials are so stable and resistant to interference, we could also create biocompatible implants that could monitor and regulate bodily functions with unprecedented precision. Imagine a pacemaker that never needs replacing, or an insulin pump that responds perfectly to the body's needs.
It's amazing to think that we could have these devices working seamlessly within our bodies, keeping us healthy and extending our lifespans. But I have to ask, what about the ethical implications of all this? Is there a risk that these technologies could be misused?
Oh, it's crucial to consider the ethical implications of any powerful technology. We need to ensure that these advancements are used responsibly and equitably, and that's a conversation we need to have as a society as these technologies continue to develop.
You're absolutely right. It's not just about the scientific breakthroughs, but also about how we choose to use them and who benefits from them. Okay, so we've talked about computing, energy, medicine, and touched upon some ethical considerations. What about transportation? I remember you mentioned levitating trains. That sounds pretty futuristic.
Yes, the potential for frictionless transportation is incredibly exciting. Imagine trains that glide effortlessly above the tracks, powered by energy recovered from their own motion. We could eliminate the massive energy loss we currently experience due to friction, creating a transportation system that's both incredibly efficient and environmentally friendly.
So we're talking about a future with silent, super-fast trains that consume almost no energy. That sounds like something out of a sci-fi movie. But let's be realistic here. We've been talking about all these incredible possibilities. But what are the real challenges in bringing these technologies to life?
You're right, there are some significant hurdles to overcome. One of the biggest is the need for extremely low temperatures to achieve these zero-entropy states. Right now, maintaining those temperatures requires incredibly sophisticated and expensive equipment.
So we basically need a super freezer the size of a building to make this stuff work.
Yeah.
That doesn't sound very practical for everyday applications.
Not yet.
Yeah.
But scientists are making remarkable progress. They're exploring ways to achieve similar effects at higher temperatures, even room temperature in some cases.
So there's hope that we could eventually have these incredible technologies operating outside of specialized labs.
Absolutely. And that brings us to another challenge, coherence. It's the ability of these materials to maintain their unique properties over time. Right now, coherence times are often very short, limiting the practical applications. However, researchers are working on ways to extend those coherence times, making these materials more stable and usable in real-world scenarios.
So it's a two-pronged challenge. We need to figure out how to make these materials work at more practical temperatures
Yeah.
and for longer periods of time. But despite these challenges, there seems to be a lot of optimism in the field.
There is. Many experts believe that by 2050, we'll see significant advancements. Imagine room temperature quantum computers, perfect energy storage devices, lossless power grids, and revolutionary medical devices, all based on the principles of zero-entropy materials.
Wow, 2050, that's not that far off. So we might actually witness these seemingly impossible technologies becoming a reality within our lifetimes. It's a pretty mind-boggling thought. We've gone from the basics of entropy to the potential for a future that sounds like something out of a science fiction novel. But before we get too carried away, let's take a moment to recap everything we've learned about this fascinating world of zero-entropy materials.
Yeah.
Where do we go from here? Okay, so let's bring it all together. We started this deep dive talking about entropy, that natural tendency for things to go from order to disorder. It's a concept we see everywhere in our everyday lives.
Yeah, and then we ventured into this quantum realm, where at these ultra-low temperatures, a totally different set of rules comes into play. Atoms settle into their lowest energy state, ground state, and those strange quantum phenomena we talked about, like zero-point energy and quantum tunneling, they become dominant.
Right, and that's where we encountered these incredible zero-entropy materials, like time crystals and topological materials. Time crystals, with their perpetual motion without energy loss, and topological materials with their unparalleled stability. They just seem to defy the very laws of physics as we know them.
And these materials, I mean, they've opened up this whole world of possibilities, especially in fields like computing, energy, medicine, and transportation. I mean, we've talked about quantum computers capable of solving previously impossible problems, batteries that never die, ultra-precise biosensors that could revolutionize healthcare, and even frictionless transportation systems.
It's a future that sounds both incredibly exciting and a bit daunting at the same time. And we also discussed how these powerful technologies raise some pretty important ethical considerations as well. I mean, we need to be mindful of how these advancements are used and ultimately who benefits from them.
Oh, absolutely. The societal implications of these discoveries are profound. And it's crucial that we have these open and honest conversations about the potential benefits and risks, ensuring that these technologies are developed and used responsibly.
As we wrap up this deep dive, I keep coming back to this idea that we're not just talking about bending the rules of physics,
Yeah.
but potentially rewriting them. I mean, what does that even mean for us, for the future of humanity?
That's a really great question, and it's a question that's going to continue to unfold as these discoveries progress, but I think it really highlights the incredible power of human ingenuity, our capacity to just push the boundaries of what we thought was possible. And it's a good reminder that with this power comes a great responsibility to use it wisely for the betterment of all humankind.
So, dear listener, we leave you with that thought. What kind of future do you envision in a world where the seemingly impossible becomes possible, where the rules of nature are not just bent, but rewritten? The journey into the world of zero-entropy materials is just beginning, and it's a journey filled with wonder, challenge, and a profound sense of possibility.